Welcome. It's a great pleasure to introduce Chris Parnin from Georgia Tech. So Chris is a researcher in software engineering and HCI, and he's trying to answer the really big questions about software engineering. We understand that when programmers are trying to build a piece of software or to use a tool effectively, they go through some mental processes. What are those? Why should we believe that the ones we've described are the ones that they actually follow? So Chris has actually done research to try to answer those questions. He'll be telling us about that exciting work today. Thanks, Chris.
Okay. Thanks. Hi, everyone. If you want to interrupt me during the talk for clarification questions, go ahead. And I'm sure we'll have a nice discussion afterwards for more detailed questions. But just to get started about me, my family came from Cuba, and we started with nothing except an egg refrigerator unit that got converted in my grandfather's house. And that's how we eventually were able to make some money and survive from that. And throughout my whole career, I've had to kind of keep working full-time just to pay my way through school. So that's kind of been my roots. And from that, one of the things that I really enjoy doing is cooking Cuban food. The funny thing, though, is I recently had a big change in my life. So I have a son, and it changes everything. I have a whole new definition of what interruption means. For example, we had to pick him up from daycare because he had a fever and spend a couple days with him. And then the next week, we got snowed in Atlanta and spent the next week with him. And so then it was 2 weeks later before I can get back to my job. To me, that's the real type of interruptions that I'm experiencing all the time now. The funny thing is, I really like Cuban food, but now I'm kind of sticking with Costco food because it's much easier. And just some background. So like as I mentioned, I've been developing for over 10 years in industry, mainly in the defense industry. And one of the things that really attracted me to research was the chance to study developers and work on problems that I've personally experienced in my time working as a programmer, and really be able to help programmers out, because there's not that many people that research programmers. And I felt that I had this chance to kind of bridge those two worlds. And so over all this time, I've had the chance to either do studies or work with various organizations and be able to do internships with places like Microsoft Research, et cetera. And just to give you an idea of what my general research approach is, I like to take systematic problems that are in software engineering and actually think about the pain points that developers really have and hope that if we could solve them, that this is actually going to really have broad impact. Because it's not just a one-off problem, but this is something that practically every developer faces. And so just to give you some examples, I've looked at the topic of crowd documentation. So we looked at this idea that documentation used to be in the form of books and asking colleagues. And we also used to have like nice published set of manuals. And that's slowly shifted over to just Googling for things and looking for the answers. The thing is, the official documentation is still out there. But now we're being outcompeted with other sources of information. It turns out that there's this whole world of crowd-generated documentation, things that are on Stack Overflow, blog posts, that are dominating how people learn about programming. And so we found that when you look at browser history of developers, they actually will favor places like Stack Overflow versus official documentation. And this is something that industry has reached out to me on this topic. And this is actually impacting how they engage with their community and understand why aren't people reading their documentation and what role they can have with places like Stack Overflow. Just to give you an example, Android recently had some features that they decided to obsolete in the next version. And it turns out that people on Stack Overflow were recommending the use of that method. And what ended up happening was that ended up getting copied and distributed throughout the whole ecosystem. And developers end up being really pissed off that they turned this off. and there was no bridge there. So that's sort of the things that I tried solving here. I've done other work also in the terms of what programming tools that people use and the programming features, language features that are available, things like generics, refactoring tools, and also some research approaches. And we've done a lot of work in just kind of understanding what does it take to pick up a new feature, what are some of the barriers there, and what are some of the usability issues that are stopping people from traction happening. But for this talk, I really just want to focus on interruptions and mental load. So the rest of the talk is really just going to go through these issues. And just to give you an idea of what this whole talk is going to cover, we know from other research that interruption at moments of very high mental load is the worst time to interrupt someone. That programmers are a little bit different than the most other office workers. They tend to have to think big about things for longer periods of time than other type of workers. And this causes them to be more susceptible to interruption. And one of the things that we're able to do is look at some of the literature in cognitive neuroscience and be able to reason about these different types of memory loads that programmers have to carry. And we could address weaknesses that humans have when you have to do these sort of tasks and build tools that help address those weaknesses. And finally, there's some exciting opportunities to use new techniques like fMRI to better understand some of the future, some of the mental load that people have. So I just wanted to give a little bit a little bit of motivation on why we study interruption of programmers. I think one of the primary reasons was to arm programmers with data. It really felt that programmers were put in situations where they couldn't say no to management. And just to give you one example, there's one programmer talking about a really micromanaging manager that was always wanting to check on what they were doing, but they went a whole nother level. They started demanding that a time study be performed with the programmers, that they actually had a consultant come in and they were going to call all the programmers in this team every 30 minutes to ask them what they were doing, and this was for 30 days. And so this is something that all the programmers were up in arms, but they couldn't really explain, well, why is it that you can't just keep working? It's only every 30, 20 minutes. And from the other side, we want managers to be able to reason about what policies that they're going to have. If they're going to have an open office, what sort of different expectations might they have on their team's productivity? And one example of this is this kind of divide we're seeing in some companies. We have companies like Yahoo that say that remote working is causing collaboration to go down, and it's not worth people being able to remote from home, because even though they may be more productive, it's not in our value system. On the other hand, we have other CEOs that say that the office is where we go to get interrupted. This is not conducive for doing real work. Sure, you could do meetings, but programmers really need to do a lot of mental work, and this is not happening in office environments. So we don't have evidence really either way to guide these sort of decisions. And for the interruptees themselves, we want to be able to help them actually recover from interruptions. And the thing is, if you look at what programmers are doing right now, they're probably using avoidance as the main mechanism. And so they use things like wear headphones, go to coffee shops, work late at night, or they try doing things like make sure their tasks are really small so that they're not ever interrupted. And if you think of the extreme of this, I mean, just how much isolation can we have before collaboration really becomes an issue? The other thing that we're seeing is we're seeing people taking extreme measures. They're saying that I'm starting to get in my 30s and I'm not able to focus anymore. Like I could work on something for 15 minutes and then I just lose concentration. And so I started taking some nootropics, and all of a sudden I'm banging out code for 3-4 hours in a row, where I used to be like every interruption would cause me an hour of lost productivity, right? So do we really need to have programmers resort to these sort of things to be able to work in our modern workplaces? Finally, for scientists, we've been using basically theories that came from the 60s on memory to kind of build tools for programmers. And not much has changed since then in the research world. I think there's a real good time to revisit these sort of models. And one of the things that interruptions allow us to do is it allows us to reason about the different types of memory requirements that programmers have. And so if you just want to generally think of the sort of context that a programmer has in mind, there's this good comic that kind of shows that even with a simple line of code, that it brings all sort of other mental state to mind. So in particular, they're looking at a flag that sets a parse tree logic in order, and there's all sorts of regular expressions that they're managing, even connects with some of the, this is in particular parsing HTTP requests, and so they're thinking of that domain, as well as things like what are the other people working on the commits that have impacted this code. And the thing is, even a simple question could cause all that to collapse, right? But the thing is, we really don't know what the space of mental load works like. There's this huge space. It's really difficult to reason about this. So that's, again, part of the reason why we need better models of thinking about this stuff. Just to give you a definition of what I mean by interruption, I simply mean to stop working. So if I am going on a coffee break, or if someone asks me a question, I am still stopping what I'm doing. And we could think of this also in terms of like multitasking, right? So there's frameworks for reasoning about how I switch between tasks. So you could say that I don't often drive while I'm programming, but I might cook and then program. So this is task switching. Each switch is an interruption. As I have to let go of one task, I'm moving on to the other, right? So I'm stopping work. So there's a good set of studies on general place office interruptions. So they find that most tasks are interrupted, and that when people are interrupted, they often take twice as long to do that task, and they have twice as many errors. We do know some things to help reduce interruption. So we know that if say a telephone is ringing, if you use that time to kind of prepare for an interruption before addressing it, you do have what's called this interruption lag to address, unload some of your context before doing that task switch. But there's a limited amount of effort. There's a limited amount of room that we have for this sort of stuff. We know from studies of different types of task work, things like editing a document versus video editing and programming, that programmers had the longest time to transition from periods of high workload to low workload. And we also know that interruptions can happen for a long period of time, that developers are often blocked by other workers going on vacation or waiting for them to check in code, and this stops them from not being able to do the tasks that they want. And there's very fine-grained studies that show that if you are doing a task that requires a higher level of mental load, you can actually measure the size of the pupil to correlate with how much effort is being put into that task. And they find that if you interrupt someone while they have these higher levels of interruption, that's the worst time to do that. And there's lots of other studies like this that find similar effects. So one of my goals was to actually start collecting some data in relation to programmers, because we know from the previous literature, some of the factors related to interruption. But a lot of these studies were done in the time scale of minutes and even seconds. So interruptions were very quick and short. And I didn't really think that fit in with what most programmers were dealing with. They're dealing with these longer term type of interruptions. So we wanted to be able to do an exploratory analysis behind this. So what we did was we collect IE usage data. So we looked at the programming environments that developers were working in, and we just collected everything that was happening. We looked at when edits occurred, when they navigated, what commands they used, when they refactored, when they were debugging, and where they were in the code, what files were they viewing, et cetera. And we had this data for 86 programmers. This was over a couple months of history each. And then we also did additional surveys with programmers so we can get some background about what sort of strategies that they use for recovering from interruption. And so the analysis that we did was we essentially looked at all the events that we collected and tried grouping them into sessions. And I'll give you some examples of how this looks like. And we looked at an interruption as anytime there was a break in this work. And for a measure of cost, we looked at how long it took for people to edit again. So in particular, we looked at sessions where people were making edits. And then as kind of an exploratory analysis, we looked at what people were doing before they made that edit. You know, what was it that they were trying to do to recover in rebuilding that context? So just to give you an idea of what a session looks like, we have this measure of focus, which basically kind of shows if you do more events in a row, it kind of builds up, accumulates this kind of like exponential growth. And if you stop working, it then does an exponential decay. So it just gives you a general sense of how much clustering there is of events. But it's a good way to kind of see 3 different sessions that are here. And so we can kind of look at how a programmer's day might look like. So we add to that focus the edits that are happening. And we could start observing some things. So one thing that we saw very often was there was this kind of like warm-up session where people didn't do any editing, but they just kind of were looking around and then just kind of went off to check email. This is stuff that we've seen in other studies of interruptions where people, they kind of like prime themselves for doing the task but just don't commit to it and they come back later. But finally, this programmer gets back into focus and they start editing. But then what we see here is that at some point they either reached a roadblock or there was something that happened for them to stop working. And that it takes another 20 minutes for them to get back into editing again. And so in general, what we just wanted to be able to do was look at things that were happening before people were making edits. And we looked at things like where did they navigate to, whether they had compiler errors that they're looking at, if there was source control events, whether they ran the program to see what the output was, these sort of things. And you can get a sense of like the kind of good and bad days. So here you see someone that's been programming for almost 5 hours straight. This is insane. I mean, this is probably very rare. We might see something like this once or twice a month. Most programmers don't work like this. This is probably closer to how most programmers work. We see just lots of little sessions, lots of kind of stop and go. We do some work. It's very, I'm sure that most programmers would rather work less and just have really nice days. So when we looked at this in total, we had over 10,000 programming sessions. And we were able to kind of generalize this. So we saw that on average that it was 10 to 15 minutes to start editing code after you were interrupted. And when we looked at specific cases of, say you were editing a method and then you came back to continue working on that, that only 10% of the time would people able to resume that editing in less than a minute. Basically, the more typical case was that people would come back and navigate to lots of other files and then resume editing. And again, if you looked at just kind of how often people got to work, they were lucky if they had 2 hours that was uninterrupted. And most of the time, that didn't even happen. And so looking at some of the common things that people were doing, we know this from the surveys that a common strategy was to kind of prune context. So I don't need to know what all these tabs are, so let me close some of them. Let me highlight a region of text that's going to be important to me. Let me mentally rehearse some of the identifiers I want to remember, take notes. But in terms of recovering from interruptions, that's more kind of preparing for an interruption. This is recovering. Most people just navigated around before editing. So they just kind of ad hocly were revisiting their code base before resuming an edit. Other people use things like inserting compiler errors. So they really wanted to be able to remember something. So they inserted a compile error as kind of like a roadblock that they had to see this reminder. And And finally, if they just couldn't remember what they were doing, they used source code diffs, that they just were trying to have a last resort way to see all the changes. And the thing was, we observed a very strong correlation between the data that we observed in the sessions and the surveys. So if people said they do this the most, they actually did it the most in the data. And so to kind of help confirm some of this, so that was kind of a good way to explore the data. We wanted a little bit deeper way of looking at interruption on the small. And so what we did was we looked at subvocalization. So it actually turns out that reading to yourself is a relatively new human invention. It used to be that we read aloud and we didn't know how to suppress our speech. And so what has recently happened relative to humans' history is we were able to read silently, but we're not completely suppressing that signal. What's happening is the premotor cortex still primes all those kind of mouth, larynx, lips muscles as you're thinking about these sort of stuff. So you could actually still measure these. So this became like of another way to be able to measure when people were thinking about these sort of tasks. And there's lots of studies that date back even 100 years ago where we know that there's certain tasks where people tend to do subvocalization than others. And we found that we were able to correlate this with other studies that found the worst time to interrupt a programmer. We found that editing was particular high time for subvocalization, that whenever people were doing heavy navigation and searching, or if they encountered a particular difficult block of code, that was when they had also high levels of subvocalization. So this became a nice way for us just to be able to confirm that the data that we're seeing in the sessions did map with some of the mental load measures that we could observe in practice or in humans. And so a recent development was that there was this company that saw some of this work and they wanted to commercialize it. And so what they essentially do now is they sell you this idea of instrumenting all your habits, and they tell you all sorts of metrics about how you work. They tell you how often you are in focus. And the thing is that this data is much larger. They have thousands of programmers and over at least a year, and we're finding very similar results to what I've had. And again, they see that people they have this metric in focus for a total of 2 hours a day. Again, similar to what we've seen before. So that gave us an idea of what programmers had to live with and in terms of interruptions and what they were doing about it. But it seemed that most of the things that they did were very ad hoc. There wasn't actually anything that seemed really smart about it. And so one of the things that we wanted to do was, can we do an exploratory analysis, an explanatory analysis of what programmers are really having to deal with when they do particular programming tasks. And so to do this, we did a literature review of neuroscience findings related to memory. And we then examined all sorts of studies of programming tasks, common reasons why they failed, some of the errors that they made, and some of the aids that they relied on. And then what we tried to do was take a synthesis of all this and be able to explain why there's different memory loads for a particular task. And so essentially what this turned into was building a conceptual framework for interruption for programmers. The problem with this was I had this huge amount of literature to deal with, hundreds of papers that I've read, multiple courses that I've taken, and what I really needed to be able to do was explain this to people that aren't neuroscientists. And so essentially what the conceptual framework does is it looks at 5 different memory types that are just kind of characteristics of the type of task that people do all the time. And then we looked at common reasons why these memories fail. The ones in bold I'll talk about. And then we relate why different tasks that programmers do tax these particular types of memories. Now I'll mention refactoring and code review. And we devised these conceptual aids that would help people recover from these memory failures. So to kind of help explain this framework, I'm actually going to go with a metaphor of how making a pie is a lot like making a program. And so, one of the things that I want to do when I buy a pie, or make a pie, is that I want to go to the store buy some ingredients, right? And so one of the things I need to do is I need to, at the store, form a perspective cue of like when I see an apple or when I'm at the store, I need to do this action, right? The thing is, if I get interrupted during this time I'm at the store, when my wife tells me, hey, go get some milk, we ran out, then what I end up doing is bypassing that path I was intending on taking. I never encountered that cue, and so I have a prompt failure. I just failed to notice this cue in the environment. The thing is, as I'm leaving the store and driving in the car, I also have a second failure. I failed to track that I had this perspective goal, right? So it's kind of like you always remember after you needed it. So these are two different types of failures that we experience. So now that I came back to the store and I'm starting to pick some apples, I noticed that there's this kid licking the apples. And I'm like, oh my God, it's gross. And so I'm trying to track which ones did he lick. The thing is, I could have a limit failure. The kid just licked too many, I can't track it. Or I could just have a concentration failure. If I went to another aisle, the ability to track that is gonna be over a very short period of time. So I finally got home. Hopefully I got stuff that wasn't too weird. And so I have this nice recipe loaded up on my iPad, and I'm ready to start making my pie. The thing is, my power goes out. And so I've read the recipe before, so I kind of know what's going on. So I think, well, I could just maybe look it up again, but I forgot where I got it from. So I can't do that, so I'm going to have to recreate it from what I saw. And it turns out that as I'm making this pie, I forgot to roll the dough out, and it results in just this terrible pie, right? So you can see that, again, we have different ways of not only remembering the events of things, but we can forget different details, like the context that we retrieve stuff. And I just wanted to do these two memory types very briefly. Essentially, we have this very interesting gradient of associative memory to conceptual memory. So in some sense, associative memory is a novelty detector. If you saw a blue apple, you're very likely to remember this sort of thing. Versus if you saw this regular apples, there's little to trigger this, right? So there's all sorts of studies that show that particular events are likely to cause you to remember things for long as a period of time. Things like spatial navigation, all that sort of stuff, has different lifetimes that you retain it. The thing is, we actually can measure how long that typically is. Usually there's 3 stages of associative memory. The first one usually only lasts a couple hours, the next one a couple days, and the one after that months. And so there are different ways to know how long you're likely to remember things associatively. The thing is that conceptual memory forms from these associations. So over time, you consolidate these memories into other parts of the brain where they're retained outside of this initial staging area. So that helps us kind of reason about some time frames of memories. So if we look at some programming tasks, I wanted to point out 2 types of tasks. So if we look at something like a systematic change I want to make to a code base, say, for example, I wanted to convert from 32-bit to support 64-bit in my code base. The thing is, that's going to require an incredible amount of locations that I have to attend to. And if it's a systematic change, you might think that I could just kind of make one at a time, and as long as I could track where I left off, that I might be okay. The thing is that in programming, this is never that straightforward. You might have a situation where I'm making a change somewhere, but it happens to be in a thread, and that threading library doesn't have 64-bit support. And so now I'm having to worry about, well, that place doesn't support it, and as I have other hundreds of locations that I'm having to track in mind, right? And so we know that when people do tools like do tasks like refactoring and use refactoring tools, one of the biggest barriers to using refactoring tools is that they maroon attention. What they do is they they bring up this dialogue and they say, you're going to want to make this large systematic change, but you don't have this ability to have touch points, all the places that I'll be thinking about impacting. You're forced to think in this dialogue. And that's one of the main reasons people just don't use refactoring tools. Another type of task that people do all the time is review code changes. And this is in many contexts. So something as simple as making a commit message. I need to recall what I did recently over the past couple of days, maybe the last week. And we know that people are actually really bad at remembering these things if they just do it freely, if they don't have any context. And we found that, for example, people forget all the time that they actually did some refactoring work when they note their commit messages. Another common scenario is if I'm going to make some changes to a code base and I want to confirm with another developer what I did, I need to be able to relay at a high level all the impact, all the source code that's being impacted, and make sure that I'm giving a high fidelity recall of that. And we had one example of where what was happening was people were constantly having to revisit old code changes because they needed to do a code review after a sprint had completed, which is basically a 2 or 4 week unit of work in most programming environments. And it's basically been a month since they've done that task. And so they had to spend all this time trying to remember how they did it. And the thing is, if you just look at source control, it's split across all these commits and other people's commits, and trying to reconstruct that, being able to look at a particular commit, see one file at a time, was just really cumbersome for them. And finally, another common thing is people like to hand off tasks or create a blog post about what they did recently. And what we find all the time is that programmers spend many hours trying to create a blog post because they're just trying to remember the order that they did all these things and find all the relevant code snippets for this. Finally, we saw this example of this older programmer that used a running Word document to just track all these locations because they simply couldn't remember what they did. So every time they did something, they just kind of created a little working log where they manually pasted in the Word doc the code they visited, any kind of screenshots that were relevant. So they were kind of just doing this manually. So one of the goals was to be able to kind of take all these insights we got of just looking at how developers really work, some of the insights that we got looking at the neuroscience literature, and say, can we start building better tools? And so just as a quick way to contrast what developers have, I'm going to show you what developers have currently in terms of current programming environments. And then I just go into 2 tools that we've prototyped and evaluated. All right, so if you want to look at a standard programming environment, these are some of the standard elements that you'll see. So we have things like tabs and trees, and these are largely attentive aids. They allow us to track all the places that we've been at. One of the things you notice, though, is for a common project, there could be lots of locations to look at. I'm scrolling as fast as possible. It still takes me 13 seconds to go through that tree. So, I mean, there's a lot of things to keep in mind. And we already know from other studies that tabs are very terrible at keeping attention on what locations programmers want. We do have things like associative queues. Developers use things like scroll bar locations to associate where something is in the code. So they just know that, I don't know where that code is conceptually, but I know if I scroll down that percentage, that's where it is, right? So they form these sort of aids. The other thing that programmers do is they use perspective tools. They make to-do notes. They intentionally put compile errors, but these are terrible things. I mean, for perspective aids, if you think of like a compile error, it's a terrible way to be able to switch to another task. Now I've broken my code base. I can't run test. I can't do anything else. I mean, it's really kind of a ad hoc solution. And finally, episodic tool support. This is what developers are using. They're using source control to kind of review all the things that they've done in the past. And I just wanted to give you a quick example of how you could tweak an environment just to provide better perspective support. So one of the problems with things like to-dos is that it's very isolated to one place. So like that apple, if I don't run into it, I won't remember to do that action, right? And I'm likely also to have monitoring failure. If I'm not keeping this in mind, then I won't remember to do that action. You know, the thing is about prospective memory is there actually research that shows if you have lots of prospective memory items in mind, it actually degrades the performance of your task. So this is something that we don't want to be tracking in our mind all the time. So just give you an example of a little video that's playing where, and forgive the encoding, it looks like really twitching here when I'm typing. But I basically have a way of attaching reminders to the viewport. And this is something not only available in that file, I can make it so that it's available everywhere. So we start having these ways of escalating information to other places so that we're more likely to encounter it if we want. But one of the things that I was mainly focusing on was episodic review. So since we had this infrastructure for collecting events, we really wanted just to make looking at source code history a lot easier to use. And so one of the things that we did was we had this infrastructure for recording every time that a change occurred and just commit it to something like Git so that we can have an actual time order of events. And then we can associate it with other things like navigation event, exceptions that occurred, if I visited a blog post, et cetera. So now we have this kind of complete history of how things were done. And one of the things that we're seeing is that the episodic retrieval is very effective for when associative memory fails. So if, for example, I didn't remember where something was, or I made a change somewhere, I could use other things like, well, it was related to that exception that occurred, so let me look in that timeline for it. All right, and so here's how we did some evaluations on these tools. And right now, I'm mainly presenting some studies on the episodic review, but we have some more ongoing studies on some of the other tools. And so one of the first studies that we did was we just wanted to compare an existing tool, Myelin, that allowed you to track different locations in code with an episodic tool. And we wanted to give a better idea of how this might help a programmer recover from interruption. And so what we did was we had 14 programmers, and we gave them 3 programming tasks, basically to make changes in a video game. And they could take notes during the task, but one of the things that they had available was they had one of these resumption aids for when they came back. So what would happen was they would start on one of the tasks, and then they were automatically interrupted and forced to move on to the next task. And they had about a minute to prepare for the switch, but this kind of was a memory stress test for programmers. They had 3 tasks to go on simultaneously, and they had to return and finish them. And so some of the findings that we had were that if they had either of the resumption aids available, they were able to complete twice as many of the tasks than people that didn't have the resumption aids. That they also had experienced less errors. So one of the common things that would happen is people took notes about what they were doing, but they were only forward-looking. Like, here's what I was currently doing, not more than 1 step forward or 1 step back. And so what would happen is they would come back, they would complete what they were working on, they would finish the edit they were working on, but then they would realize that now that I finished this edit, I need to go backtrack to where I was before and continue hooking up code. And what would happen as a result is they forgot what that place was. And so they would spend the rest of the time just trying to relocate places they've already been. And this was something very frustrating for them because there was many cases where people just timed out for the task because they spent the next 5-10 minutes relocating code that was something they just were playing with just a couple minutes ago. And a lot of this was related to their incomplete note-taking. The other thing we found was that participants were using the memory aids very differently. So the tentative view basically showed where they had visited or not visited. And the interesting thing about that is when they bolded these locations, they didn't have any particular associations with it. It only just directed their attention. So these really weren't associative aids. They didn't have a sense of what was there. They just knew that they could click there. And so that's what they did. And it just increased their chance of revisiting something, but they didn't really know what they were revisiting. The episodic tool was used differently. They actually did use a kind of backward walk in what they were doing. They reviewed the steps that they're trying out and were able to kind of reach a point where they're comfortable at restoring their state. It was nice that we were able to see some of these things happening in a controlled setting, but we wanted to be able to see how this would be used in an actual programming task. And so one of the things that we did was we visited a site with 11 developers, and they were split across 3 different teams. And what would happen is that we wanted them to tell us about what they were doing, just walk us through the task, as if they were going to hand the task off to us, or if they just needed to explain, for example, if they wanted to confirm that the changes were okay. And the way that we did this is we used a tag-along interruption. So what I mean by this is I didn't intentionally interrupt them. What I did was I waited for them to get back from a meeting, or if someone was coming by and stopped by them, and I'd wait until they left, and it would come up real quick and they're like, hey, would this be a good time to look at what you were doing recently? And so I felt that was a nice way to get kind of like a realistic scenario to kind of inject studying this tool. And what we did was we had just different episodes of comparing people using free recall, and this often just was them using their own source control views versus using this new tool that they had. And one of the things that we saw right away was that there were a much richer report being given to us when they did the episodic review. Basically, people stuck to a very low-level, high-level description when they just did free recall. They just kind of told me, kind of from the goal level, this is my goal, this is the task description. I probably could have got the same context just reviewing stuff in their agile trackers. Versus with the episodic review, they were really getting at different issues that they were currently coming across. They were explaining these sort of things to me. They were explaining different solutions and strategies that they had. They were basically able to start recalling things that even weren't related to the edits. They were having a conversation with me. They were actually able to recall all these changes and relate them to me. The thing, though, is that there was definitely a little bit more effort in the episodic review. And it wasn't where you would expect it to be. For the most case, they were doing about the same in time. So that most reports could happen less than 5 minutes. The thing that was happening was for the free recall, a lot of time was just wasted in using the source control. Like they were trying to bring it up and realize, well, I just committed something, so the views I thought were there, the state that I thought was there wasn't, so let me go and dig through it. And they just weren't as skilled using it. The other thing that would happen on the other end, though, was with the episodic review, it would bring up a lot of refactoring changes that they're doing. And so if I made a change across 30 files, that's a lot more changes to review. And so basically what was happening was there were a couple cases where the tool wasn't being able to filter out some of these things. And there were kind of things that if we put more intelligence, you can kind of filter these things out a little bit better. And then in fact, there's some good research on being able to identify systematic changes where you can just kind of collapse these things. But for the context of the field study, we just kind of wanted to get an idea for how often those type of situations did occur. So it definitely was a barrier to using this tool, but it seems that for the most case, we could do this review within time that was typically smaller than what they would do if they were just futzing around. And the other neat thing was as soon as they did this review, they went right to work. So there wasn't like this additional edit lag. It really did help them kind of reload all the stuff they needed. So after doing this work for many years, I decided to publish a blog article just kind of describing some of the findings that I had. And the response I got back was immense. So this happened last year in January. And it's still almost every week I still get someone email me a story about interruption and telling how this has helped them out, how they're pasting this article out on their doors. how that one person wasn't allowed to wear headphones, and after this article came out, the CTO bought the whole team headphones. That there are some companies that are instituting offline hours so that they have no meetings, like say on a Thursday. And even though I just made some of these tools, this kind of a simple prototypes, I'm already getting thousands of downloads, which is not crazy. I'm not actively promoting it, but I mean, it's much better than any other tool I've ever made. I mean, I've made lots of tools, and I get like 5 people to try it. So I mean, this seems like it's promising. And we're starting to get some researchers to use this for designing experiments, in particular in spatial editors. So there's lots of competing things like code bubbles, code canvas, and they didn't really have, at the time, a way to reason about what the tools were doing. And it turns out we were able to say that some of these tools are supporting a conceptualization of spatial memories versus the others are supporting associative memory of spatial memories. And we're able to show that that's why one is working another way versus the other. And so this is just the article. It got published in multiple magazines, and we got over 300K visits over the period of time. But at this time, I just want to get a little bit more into what's next, right? One of the stories that was coming across was someone was talking about how they were working with this expert right next to them, but they felt this struggle every time they asked him a question like, I know I'm really disrupting this person, but I really don't know how to do this task. And so there's this trade-off of like, I want to be able to transfer knowledge between people in a much more streamlined way, but can we do it without having to bug the expert every time? And so some of the stuff I've looked at is being able to take some of the recording that I have of how people have done these programming tasks and be able to replay them and kind of summarize them a little bit better so that an expert could just do the task, optionally provide some annotations, and then share it with a developer. And just as an example, I've done this for my own, I start doing this for my own blogging posts. I'm one of the few people that know how to do Visual Studio plugins. And so my blogs are widely read on this articles about how to do certain actions. And it used to take me an hour or two to do this. Now it takes me 15 minutes, 30 minutes at tops to do these things. So I definitely noticed my own thing. How this is better. There's ways to think beyond programming environments. So I just wanted to give a really quick example. Look at IE6. It didn't even have tabs back in the day. So we could do this little thought experiment. How would you better support memory support in a browser? So it used to be you just had one location. How would you track more than one? So we added tabs. So now we could attend to many places. But now if I have lots of tabs, it's very hard to focus on them, right? The thing is, as soon as we add associative cues, then all of a sudden I make it easier for me to swap in and out of my attentive memory a little bit larger stuff. The funny thing is programming environments don't even have icons. That's one of the simplest things we could do. It'd probably be hugely productive. Another thing we could do is add perspective reminders. So I have this little tool that will change an icon in a tab, and it'll tell you, hey, you have some reminders set on this web page. It's a very simple tweak. The other tool I have is something that looks at all the developer-related sites you visited, and it lets you retrieve something that, like I know last week I found this article that was very useful. Let me look it up. And so it's another way to kind of reason about locations using this framework. And the thing is, this environment's only getting richer. There's a student in the UK that has been using this framework to reason about a smart bag for perspective reminders. And just think about if a programmer had classes, what would their programming environments look like? But that's kind of easy. What's something a little bit bolder? One of the things that has bothered me as practicing in software engineering is we're still kind of a young field. There's a lot of absolute claims being made. So we have things like large methods are bad for understanding. We have to break them up and make them really small. Or we should be teaching object-oriented programming, or functional programming is the best way. Static languages are better than dynamic. Visualizations are better. That there's even the situation of where there's new law that's saying that a programming language is like learning a foreign language. So we have all these kind of statements, and they're not being tested in any ways. And we have empirical ways of evaluating them. And I've done a lot of research doing these things, but I think there's limits to how well we can answer these type of questions. So one of the things we've been looking at is kind of thinking about the neuroscience of programming. So how can we, in general, look at insights from neuroscience to have a better systematic understanding of how programmers work? And so we've done the first study of programmers in the fMRI, and we're able to demonstrate that we can do a simple experiment where we could see what it takes to understand a code snippet. And we did this by comparing it with a task for looking for syntax errors in code versus a task for understanding what the output of the code snippet would be. And this is something that we're trying to pursue with other universities, so a German grant for doing this over the next 3 years. And just to give you a peek at what some of these results look like, we have ways of relating this to some of the existing program comprehension frameworks and be able to show how this does fit a little bit with bottom-up comprehension. So it gives us kind of a path forward to kind of strengthen or refute particular theories. And I just wanted to leave one example that I think that would be really compelling. So there are these examples of studies that looked at novice golfers versus expert golfers. And one of the things that we find is a novice golfer really uses a lot of effort when they think about how to swing their putt. So what we end up seeing is that experts have conceptualized this action into a single unit, and they just execute it without really thinking. How would this look like in a programmer's brain? We know there's lots of other experts, video game experts, taxi drivers. They actually change not only where they activate in their brain, but they actually show increased mass as well. So what will we find for programmers? And so we can start thinking about answering these questions. We might not be able to do it in the next 5 years, but we can at least be on the path there. Is it worth teaching programming at a young age? We know that there's a critical period for learning foreign languages. Is there for programming? Can we finally provide a neurologic basis for programming in the zone? This is something everyone throws around. I need to be in the zone, but we don't even really know what that means. There's all sorts of practices like object-oriented languages, design patterns. If I teach someone design patterns and they conceptualize this over the years, does that actually change the way the brain is activated when they see that code versus someone that has never seen a design pattern before? Can we actually show that teaching something has lasting impact? And then this is something really simple. There's a whole code visualization community. They make these claims that visualizations, visual languages reduce mental load. Does it really? And just if you want to read a little bit more, I wanted to point out that I think software engineering is going to change in the long term. I think from what we've seen that when we research something, it usually takes about 10, 15 years to make progress on it, and then another 10, 15 years for industry to adopt it. This has been the case for many software engineering tools. So if we're thinking about what we need to do now, we have to start thinking actually in the next 30, 50 years what the environments will be like. So I have an article that actually kind of speculates about this. If you have time, look at it, please. And just to quickly reflect on the past 5 years, we know that interruption at moments of high memory load incur the worst costs. Programmers have to carry high mental loads more than other programmers, that we could model how these loads work using insights from neuroscience. And we could build tools that actually address those weaknesses. And we have exciting new ways to look at understanding mental load. And this has been accumulated across, there's been other work I've published, but just related to this topic here.
We have time for a few questions.
So you showed that most programmers have 2 hours of focus a day. If you eliminated all interruptions, what would the average be? How much are we losing? What could we do?
The overhead, I think, is about 20 to 30% in terms of like the edit lag that's associated with the sessions. So of those 2 hours, about 20, 30% is wasted in recovering. We don't really have a way of knowing what it would look like if we reorganized.
So put a program in a room with
Yeah.
an isolation tank and just
Airplanes.
Yeah.
yeah.
Yeah, there could be other ways of.
I mean, I wonder if there's only 3 hours max. I mean, we're only losing an hour, or
So I think there's another thing we're running into, which is there's built-in ability to focus on attention. The thing is, okay, say there is a max, say 2 or 4 hours. We don't want to waste that 4 hours on task switching unnecessarily. So I think that's still the goal. There may be a max, but we want to maximize what that 4 hours is.
So you instrumented and looked at kind of like conscious direct work on programming tasks in the IDE. Like what about, if I have a problem, I'll do some work on it, kind of go off and do nothing or do something else, and then the solutions kind of come out later. So like, how can you look at with these creative, complex tasks, this kind of work that happens not so much directly?
Yeah, I don't think interruption is bad. I mean, I think interruption could be very beneficial. So I think examples like that do help people. On the other hand, I hate when I'm working on something and I'm kind of ran out of time. I have to go home and pick up my kid, and instead of spending time with my kid, I'm now thinking about those things. So you really want to be able to not rely on those mechanisms. And if anything, we want to be able to work in a flow-free way. We really want to be able to work with the time we have, do the task we need, be able to use these tools to pick up where we were, and not have to rely on that sort of stuff. But it's a good point.
How do you differentiate between a true interruption and just taking a break or thinking, taking a break to think and to strategize?
Right. So the question is, how did we define interruption in terms of the study? That study for us was really just an exploratory study. It allowed us to kind of see what that space looked like. And if anything, it was basically the max level of interruption that people could have. There are some where, but if you look back to what my definition was, it's this stopping working. It can be an interruption itself. It isn't necessary if it's a colleague or not. I think some of the biggest interruptions is if I'm not able to work on a task because my machine went down or I have to go to a meeting. It's not necessary that someone came to ask me a question. So the data, we could not tell that, but in the field study, we were able to observe interruptions in natural settings and kind of literally everything that we saw in the data happened in the 2 weeks at the field site. So I mean, these are grounded in real findings.
Thanks.